here. All right. So today we are going to start talking about field-oriented control. Okay, field oriented control. And I think starting with field-oriented control will be helpful when we actually look at the grand scheme of controlling a machine, because primarily there are different strategies that you can use to control a permanent magnet synchronous machine. One of the key or one of the primary methods is FOC. Okay, you can use sensors or you can use sensorless methods for this, but regardless of the approach, field-oriented control can give you really good performance. Okay. Now, we haven't discussed in detail the different control strategies, but once we understand the field-oriented control or the overall system, now we can actually see where the different components such as voltage generation, current measurement, transformation, the control system, all that comes into discussion or comes into place once you have a good understanding of this. Okay. Of course, we'll go talk about different control strategies, maybe not in this much detail, but as an overview. But I want to present to you initially the field-oriented control strategy that we can apply to PMSM. Okay, permanent magnet synchronous machines. This is also known as vector control. Vector control. This idea, well, at least as far as I know, the idea originated from Siemens back in the days for control of induction machines, and then later got adopted to permanent magnet synchronous machines, which actually expanded, proliferated over a number of applications because of that unique features that they have. Okay, and then first of all, we need to think of why we do FOC, right? Why do we need to do field-oriented control? You'll see that it has a certain complexity when you do field-oriented control or field orientation for a synchronous machine, especially for a permanent magnet synchronous machine. But there are certain advantages that we have in doing that. More specifically about the optimal torque generation. Okay, so I know we talked about the rotating MMF that's generated by the stator, the rotating flux vector, right? And then we said we have the rotor flux vector, which is based or which is established by the permanent magnets, right? So we said, oh, all right, we have a permanent magnet rotor. Okay, so maybe we have a rotor like that, which has, let's say, a north and a south, right? So we have a north and a south like that. And then for this, we can assign a vector. We can say, so the flux vector of the permanent magnet is along this north, right? We can say that. So this is our rotor flux vector. Okay, we can call this also the rotor flux vector. Okay. Now, of course, in generating torque, we learned that we need another magnetic field which is established by the stator, right? So we'll use a different color here. So you're going to have another flux vector like that. So we have A, B, and C windings, and with that we can, depending on how we how we apply the voltages and currents, we can establish a flux vector, essentially another north and a south within in the air gap, right? And we can actually orient it however we want to based on the angle of the current, the theta current. So if you remember the currents, right, we said IAS equals IS cosine omega t. Omega t is basically an angle, right? Theta. This is a theta. And we can change the theta however we want to, and we can set up our flux vector wherever we want to, right? And we're going to have similarly an IBS, which is 120 degrees out of phase, and an ICS, another 120 degrees out of phase. So with that, we showed that we can establish a rotating flux vector with frequency. But if you hold that angle constant, right, instead of changing, instead of having a frequency, you hold it at a certain theta equals theta 1, right? Once you hold it at that value, you can hold your flux vector in that alignment. It can be along with the permanent magnet flux. It could be opposing permanent magnet flux. It could be 90 degrees out of permanent magnet flux. Any position you want. You have the control to position or align your stator flux vector basically using this angle that you apply to the currents. Okay. Now we have two things, right? When we look at a vector, if I draw, let me just draw the vector like this. Okay. If I draw the vector like that, for a vector, you have two things, right? You have an angle and you have an amplitude. You have an angle and an amplitude, right? Now, how do we control the amplitude? We know we can use this angle to control how we position that flux vector, the stator flux vector. Exactly. You can use this IS to change. You can apply different voltages that will result in a different current, which in turn establishes a different magnitude of flux. Okay, so let's say we've established our flux vector in this orientation. Okay, this is due to the stator. So we'll call this flux of the stator. Okay, flux of the stator. Now I didn't draw it directly 90 degrees from our permanent magnet. Let's give this angle a name. We'll call this theta F. Theta F. Okay. Now this is a very useful concept. I think we even proved this, if I remember correctly, in one of the previous videos. We showed that the electromagnetic torque that is generated, right, the TEM, we showed that TEM is proportional to the amplitude of the stator flux times amplitude of the rotor flux or the permanent magnet flux in this case times sine theta F for a non-salient machine. Okay, for a non-salient machine. Okay, now this is a little bit of an important topic. You have heard of this now a few times, non-salient and salient machines, right? For saliency, with machines with saliency, you have something called the reluctance torque. Right? Reluctance torque. We talked about this. The magnetic flux trying to align with the shortest possible path depending on how the material is laid out in the rotor, right? So the reluctance torque has a different characteristic than the magnetic this field interaction torque. Okay, so we are not going to focus on this saliency. We will assume a non-salient machine so that we can focus on the field orientation. Once you have a good grasp of the non-salient machine FOC, applying that onto a salient machine, can be understood very easily. That gap is much easier. All right. Okay. So now we can control this amplitude by controlling the state of flux, and we can place the state of flux vector where we want, right? We can place the state of flux we want. Now, if we are to come up with an equation with this, we can say TEM is equal to, it's an inequality, this is a proportional relationship. We can say this is to a K, let's say, I'll call this K machine. Okay, it's a constant times the magnitude of the permanent, I mean, these are scalars, so you can switch them, that's fine. And sine theta f. Okay, now for this equation, all right, we have, let's say this is a fixed value, right? This is a fixed amplitude. State of flux, let's say we have set that to, we have applied a certain current and we have set that to. And with the same permanent magnet flux and the state of flux, in order to maximize that electromagnetic torque, what should sine theta f be? What should this be? What should that sine theta f be? For us to have maximum torque. Okay, very good, right? All right, 1. Okay, this has to be 1. Okay, so if that to be 1, what's theta f? What should theta f be? Exactly, 90 degrees, right? 90 degrees. So this shows us that if you are to generate optimal torque in this case, your stator flux vector has to be placed 90 degrees out of phase from the permanent magnet flux. Is that clear? That's one of the key points that we need to understand. Okay, that has to be 90 degrees out of phase. Okay, so up down, right. Yeah, so depending on how you set it, it will either go in clockwise or counterclockwise. That's right. Yeah, that's true. Okay, now what was I going to say? I lost my train of thought. I think I asked the question, right? So we place the vectors like that. Okay, yeah, so we can apply the stator flux vector 90 degrees out of phase. Now, in order to place our flux vector, the stator flux vector, to be 90 degrees out of phase from the permanent mag flux vector, what other information do we need? What do we need to know about the machine state in order to place our stator flux? Exactly, very good, right. We need to know where this permanent magnet flux vector is oriented at. How is it placed? Because when the machine is rotating, right, this could be at any arbitrary position, right? And unless we know where it is, we cannot optimally place our stator flux vector. Okay, so the way to achieve, or the way to measure how this permanent magnet flux vector is oriented is to use a position sensor. Okay, you can use a position sensor, and there are many out there. All right. So what you do is you, let's say we have a rotor like this, and then we're still working with a non-salient machine. Yeah. Right. So we have our north and south. Now, so this, let me draw this in kind of the 3D domain here. Okay. Now, so here we have our, like that. So we have the shaft attached. You need some kind of a sensing mechanism on this, right? To see where or how this motor, the rotor is rotating. This is the rotor only. I didn't draw the stator, because stator is what generates a stator flux where the windings are there, right? So we need some kind of a position sensor that mounts on. So there are different types of sensors. You can see encoders, optical encoders, and there are some subcategories among them. I won't go into that. Encoders, there are resolvers. More primitive, you can use potentiometers. There are disadvantages to using them. Potentiometers. And then you have Hall sensors, right? The linear Hall sensors that gives you precision. Okay, so whichever the case, you're going to have part of that sensor mounted onto the rotor. Okay, so you have maybe a disc that's rotating, and then there is some kind of a light beam counting, where this position of this disc is at, depending on how the pattern is laid out. Okay, so that's just encoder. It's a very simple, relatively simple. Okay, so you have part mounted on the rotor. The chassis of this sensor will be on the stator. So there's one component in the stator, one component in the rotor, and then it will look at how the disc is moving, and it will measure position, and you will get a measurement. So typically, so theta, if this is your rotor position, you're going to get a linear measurement depending on number of poles on the sensor that you can use to determine where your rotor is at. So this is rotor theta r. This is the position. Let's say this is measurement, right? Position measurement. So it's going to be a linear variation as rotor position changes. So as the rotor rotates, you're going to see this increase or decrease depending on the direction you are going. All right. So that's something you are going to see. Now, without complicating a lot more, there are some important concepts related to the position sensor that I want to talk about. When you look at a position sensor, that sensor has a zero. What I mean by that is, let me go to a different piece of paper, and I think. So as you rotate that sensor, the sensor will. So let's say we assume you are rotating the sensor by itself, not attached to the motor. You are rotating it at a constant speed, and then you're going to see that. So this is 0 degrees, 360 degrees, and then here onwards it's going to come back, right? Again. So for the new cycle, this is 0 degrees, this is 360 degrees, right? And this pattern will repeat. All right. So this is from the point of view of the sensor. All right. Now, if we go back to our rotor, for the rotor, the flux vector 0 alignment is right along this north. Right along this north. So we have to be very careful when we mount the sensor such that we align this sensor 0 position to the flux vector 0 position. Okay. And when you do that proper alignment, when you rotate, when the rotor rotates, it will accurately tell you what the orientation of the rotor is or the magnets are, so that you can generate your stator flux. Okay, so that's an important concept that you want to understand. Now, practically speaking, aligning the sensor zero with the rotor flux zero, this is a very difficult task, because you have to look at back EMF, and most of the time you have line to line voltage, and you have to offset by certain amount depending on the number of poles. So it becomes a tedious process. Okay, so instead what people do is they basically mount the rotor. So let's say this is our position measurement. They mount it on the motor, and then when you look at the true flux alignment based on back EMF, you will see that there is an offset. There is a constant offset because they are not properly aligned. So if you want to visualize this with vectors, this is my, let's say this is my north rotor. This is still the rotor. This is my flux vector, right? And this can rotate, right? This can rotate. And then when I mounted my sensor, sensor 0 was like this. So I call this theta E, electrical angle that I'm measuring, right? Now, as the rotor rotates, since this sensor is also mounted on the rotor, what do you think will happen as the motor rotates? Oh, sorry. Yep, got it. So as the motor rotates, the magnets are going to rotate. And since the sensor is mounted on the rotor, what can we say about this vector, theta E? That is also going to follow, right? So then what will happen is it's the relative difference is constant, and then this is going to follow along with it. Okay, if you go this way, it's going to go that way. If you go this way, it's going to go that way. Okay, now, however, the problem is this is what we are using to orient our stator flux vector. And if we use this as it is without correction, we have a constant offset, and we are not optimally applying or placing our stator flux vector. So can you propose something to fix this? Can we somehow figure out a way to not have that constant offset? Very good. Exactly. What we do is we figure out, okay, how much is this offset? Okay, you can calibrate that. And then every time you feed your sensor signal to the controller, you're going to say, hey, every time you read it, subtract this amount, because that's a constant, right? So when you do that, your new or the corrected vector is going to be aligned to the flux vector. So this is theta E minus theta offset. All right. So when you do that, now, even though you are rotating, right, that correction is constant, and it's following with the rotor flux. Okay, so this is a very important concept, and if you don't have that proper alignment, you could essentially result in zero torque because because of the offset is too large, you might apply your stator flux right along your permanent magnet flux, right? And then based on our equation, theta F becomes 0. Theta F is 0, torque is 0. Okay? Or you can apply negative torque. If you go in the opposite direction, you could result in negative torque. Okay, so that's something that you have to be very careful of with this offset for field-oriented control. Okay, so we have the idea of what to do here, right? Do you guys have a clear idea of what we are trying to do? We have a position sensor that will help us place our stator flux vector, right? So we know where our true permanent magnet flux is at. Therefore, now we can place our stator flux vector 90 degrees out of phase for a surface mount PMSM. No compensation, no correction as for now. Just, assuming an ideal system. Okay, so now this will give us an optimal torque from the machine. We are not wasting any energy in this case. Is that clear? You guys understand that? The idea behind it? Okay. Okay. So that's the point of view from what we are trying to do with field-oriented control. And of course, guess what? Like everything else, devil is in the details, right? So you have to pay attention to details, and then how do we implement this? How do we achieve this? There's a lot of science that goes into doing that, just to try to orient the stator flux 90 degrees out of permanent the rotor flux. Okay, so let's draw a little block diagram here, and I'll try to explain what we do in terms of a control algorithm perspective. Okay, so this is the FOC algorithm, but I'm going to draw it in like a block diagram so that all of you get an idea of what we are doing, and then we can go into the little bit of details that we have within the machine. Okay, and the overall system, and I'll try to identify what's what as I go along. So we have our machine. Okay, we have our machine here. So this is my permanent magnet synchronous machine. We have three-phase windings here. Okay, three-phase windings. Now we need a means to drive the motor, right? We need a means to drive this motor. Okay, so three-phase machine, I mean, of course, you can connect it to line voltage, right? Three-phase line voltage, but then it's just going to run at that one frequency set because the frequency is not changing, right? If you are to control the speed and you want to have flexibility of the voltage or the current that flows through, we need an inverter, a three-phase inverter. Okay, so typically this is PWM switched inverter. All right, and I'll draw like that to show the switches. Okay, it's a three-phase inverter, and we'll talk about the three-phase and PWM generation and all that later. Okay, so this is our inverter. Now, if you are modeling an inverter in simulation, the transfer function of an inverter is typically 1. Okay, healthy state, you assume this as a gain of 1. So you can assume there's just a gain of 1 there. Okay, all right. So in order to generate these PWM signals, we need to say, how much PWM for A, how much PWM for B, how much PWM for C. Okay, so in order to say what signals go into each of the legs, we have a modulation strategy. Okay, so modulation strategy. Typically, a lot of people just combine these together, but let's understand what's the basic idea. This is hardware, right? All this is going to be in software. Okay, so before that, this is going to be in software form. Right, and this is hardware. This is the inverter, this is the motor. All right, so we know we can set up the modulation calculation, and you learn more about these as we go along, because for us to apply voltage, we need to say, okay, how much voltage to apply. That voltage needs to be converted to a PWM signal. All right, now how much voltage need to be applied need to be based on where we want to go, right? How much torque do we need to apply? All right, that how much torque do we need to apply comes from a torque command. All right, comes from a torque command. I don't want to draw that there because I might run out of room here. Now torque command, TEM, right? If we go back to our equation here, TEM, which variable is controlled using, well, let me rephrase that. So we want to control TEM, right? Assuming we know 90 degrees theta, right? We are sure, we are guaranteed that we are at 90 degrees. What other variable do we have control over in here to achieve that electromagnetic torque? Assume that we are at 90 degrees here. If we are at that position, then what is the other variable that we can control here to change the amount of electromagnetic torque applied? State of flux. All right, very good. State of flux. So in order to generate state of flux magnitude, we can control the current amplitude, right? We can control the amount of current. Basically, since it's a three-phase system, you're going to have a amplitude for the current depending on the voltage we apply, right? So we can control the amount of current that we apply. So typically, any electromagnetic torque command, I'm going to use the star, gets converted to a current reference. Okay, a current reference. Now, there are different variations. I'm going to talk about the standard method here. That's the important concept. And in terms of setting the currents, how many currents do we have? How many currents that we have to control? 3 currents. So Alex is saying we have 3 currents, right? Now, this would have been the way to go, back in the days if we didn't have reference frame transformation. With reference frame transformation, we were able to convert those 3 currents to 2 currents, right? 2 currents. So what we are going to do is now, instead of going to go into that sinusoidal domain, we are going to say, hey, we have the position measurement already, right? Because in order to align our currents and voltages, either or, we need to know position. So why don't we use that position to our advantage and convert or design our control system in this reference frame itself? Okay, so ultimately your electromagnetic torque is going to convert into an IQ command and an ID command. Just the two. Okay, IQ command and ID command. Now, exactly. That's correct. So that modulation strategy, depending on what you use, will convert it back. And I'll come into that what's within this modulation block. Okay, we'll talk about that. And then how do you convert your torque command to current commands? That depends on what you are trying to do. And I don't want to get into great detail here. And because people do different things with different machines, so you can actually, you have the flexibility to do a lot of things. Okay. So let's say in order to, for that torque command, we have an IQ and an ID command. Okay. So we have, and I might run out of space here. We have an IQSR command and an IDSR command. Okay, so we have an IQ command and ID command. All right. Now, for some of you, I know you have had control systems, so this might be, this might make sense. You have a reference, but we need to know the true value before we do any regulation or closed loop system, right? Therefore, we need to measure the currency, right? We need to measure the three-phase currents. Some people just measure two and find the other, assuming a balanced system. But for now, for our discussion here, let's assume all three are measured. Okay, so I'm gonna combine them to one. So this is a line of three. So we have three current measurements coming in. Okay, now it goes into the microprocessor, and those three currents gets converted to two. Okay, remember Clark and Park transformation, and with that transformation, Ks, I believe, this becomes an IQ SR and ID SR. These are the measured value. These are the measured values. Okay, and guess what? If you have a sinusoidal set of currents here, what will these look like? They're going to look like DC, exactly. However, in order to do the transformation, what other piece of information do we need here? In order to do the transformation, if you think back on our transformation matrix, we have our three variables coming in. We need position sensor, right? So you're going to attach a position sensor and you will measure position, and that is fed here. Okay, that is fed here. This is your rotor position. That helps us convert our three-phase currents to two, and now you can calculate the error, right? Plus minus, this is similar to now our DC, right? Plus minus. So let me try to do this as cleanly as possible. This is not the best diagram I'm going to draw. Here. Okay. So we have the error. Okay, error. Now what we do is we place a PI controller. Typically that's what we did. Remember, for a DC motor, if we had DC currents, we had a PI controller that did the closed loop regulation, right? So you're going to have you have one controller for Q axis. You're going to have another controller for D axis. Typically you use only P and I, which results in what we call, these are going to be VQSR commands and VDSR commands. These are applied to our modulation strategy. Sometimes they get converted from two variables to three, which is our KS inverse, right? And depending on the strategy used, you don't even need to do that. You might have a lookup table that directly converts it to 3 and then into PWM signals, or just timings for the PWM. Okay, so now what we have here is the basic, very simple Not simple. I don't want to say simple. This is pretty complex. Now we are missing one more thing. In order to do this conversion, again we need our precision, right? We need our precision signal, theta r. Precision is needed, right? And depending on how that is, these voltages that are in the rotor reference frame get converted to three-phase voltages and then into PWM duty that is applied to the machine. Okay, is that any questions on now this transformation? With this transformation for the controller, it makes this system look like a DC motor, and then it doesn't have to deal with all the sinusoidal variations. Now you can design your controllers for or assuming the DC behavior of the machine. You're not going to see any sinusoidal current unless there are faults or you have some other issues in your measurement. Now these assumptions kind of get violated and then they move away from that expected behavior. Okay, Michael, do you have a question? I know you're trying to kind of figure out what to type here, but okay. So we need two key things here. We need precision measurement. Right? We need a precision measurement. Precision measurement of the rotor, right? Measurement. And then what else? We need the current measurement. Current measurement. Sure, yeah, I know. The first time is gonna be kind of shocking, and then you have to think about this by yourself and then understand what's really going on. Okay, but basically what we are trying to do here is, since all of this is inside the controller, right? Inside the controller, with the conversion, we are making the motor look like a DC motor with two axis control, two different DC motors. Kind of, it's it's not really a technical way to say that, but we're converting those to that rotor reference frame, making it look like DC. And with that, our regular PI controls can be applied, considering bandwidth, right? And we talked about how to use bandwidth and all that in your PI controller design. So all those concepts will apply because you can even model this motor in the rotor reference frame. We did that, right? So now you can say, hey, I have one equation for the Q axis, one equation for the D axis, and you can even assume for your model, you're measuring ID and IQ and ID directly, and you have the corresponding LQ, LD, and the resistance values for each of those differential equations. Okay, so it's going to look similar to controlling a DC motor, but now you have two differential equations. So you have two controllers. Close enough, right? Zero sequence is not generally considered because we assume a balanced system for the most part. You have a fault, you have some other nonlinearity, those things that kind of violates that rule, and then you have to think how the nonlinearities will affect your overall system. That's a different discussion. That's a more advanced discussion. No problem, Lucas. Yeah, that's fine. But this is the Yes, Alex, because if you think of the plant, right, and I don't know if you had 360, which is our control systems class, you only model your controller with or plant or the motor as a first order differential equation. So you have two first order differential equations. Yeah. So you have only two first order differential equations, which means you only have a pole, right? If you go back and look at our DC motor controls, if you have one pole, you can control that with a PI controller without going into a great deal of control theory. Right? You can control, stabilize, and achieve a very nice performance with a PI controller by canceling the pole with a zero. Very simple method to design a controller. And then you can set your bandwidth based on what you want to achieve. Okay, so that's why a PI is sufficient. PID differentiator is not generally preferred. Yeah, I understand. Yeah, so you'll kind of, it'll complete when you take 360, but different. Yeah, even I've asked the same question. Going into industry from academia, right, trying to learn these things in application, I saw that you don't need the differentiator, and I've tested with differentiator, and it doesn't contribute that much in terms of performance, because actually sometimes it could make it worse because it'll amplify noise, and now your torque starts to vibrate and all that, so it might not perform well at all, right? So generally PI controls work close to perfect in this field oriented control algorithm. Okay, I want to say vector control, either one. Very common. Different groups use vector control, different groups use field oriented control. Okay, so but in this picture there is so much hardware, there's so much engineering that goes into this, right? The machine design is a field of its own, right? Measurement, precision measurement, a field you can study that by itself. Current measurement, there are different strategies for current measurement, right? And then applying your voltages through PWM modulation, and just to get an inverter design, that's so complex, many subcomponents, sub-circuits that goes into designing an inverter. Then all the controls, right? See, within this you have so much control theory that you have to decide, a lot of mathematics that goes into doing the transformations. So it kind of ties everything that you have learned, at least most of the things that you have learned as an electrical engineer and what you will learn in the future too, together into one picture. So I really like this algorithm, and you can do so much and so many studies on this. So but very popular algorithm, very commonly used algorithm. And you can even there are strategies to eliminate the sensor by using a sensorless algorithm, using like an observer or estimator based on your current measurements. Okay, so now you don't even need this measurement, and then you can actually use an estimate. Again, that will be in an algorithm in a microprocessor, which feeds or which provides you that theta r. And there are certain disadvantages to using that scheme. We can maybe talk about them later. Okay, good. All right, so so try to understand and then think of what this transformation is doing to the variables, and how it is making the machine look like a DC motor. And when you try to think along that lines, this will be much more clear. Okay, and I even want to go to the next step, and I want to challenge you to design or build a Simulink model to do field oriented control, if you really want to understand how this is done, or how it works, you should build a model. A model for the machine first of all, and then come up with position, come up with currents, and then you can you don't need to build an inverter. You can, and then you can apply the closed loop and see if it works. Okay, and if you want to do that one cautionary step, now you can see that we are not controlling the speed here. So if you maintain a certain torque, this could speed up. Theoretically speaking, the speed could increase to infinity, right? But you have a limitation in your DC bus voltage for the inverter that we don't see here. If there is such thing, then what we typically do is we regulate the speed for testing purposes, and in simulations, we typically set the speed to a certain speed, omega r. We set the speed to a constant value, and then we try to see the performance of the field-oriented control algorithm at that speed. Of course, you can apply speed steps, change speed, and see how the controllers respond to that. But generally, you would want to regulate the speed, especially in your simulation. If you want to do that, try to set the speed, and right away it's not going to make a lot of sense to you. You might want to have like a star put next to this comment, because when you do the design, you're going to think about it, and this is going to help you. Okay. All right. So I think this is the interesting, discussion we've had. Maybe you got the idea, but if not, let me know if you have questions, and we can talk about how things done and why they work the way they do. Okay, so let me stop the recording here.